Hello and welcome to Engineering Ethics at NJIT. I'm your instructor Daniel Estrada, and this is the lecture video for Lesson 12 on AI Ethics. I'm recording a new set of lectures for this AI unit, Lessons 12, 13, and 14. I'm recording these in April of 2023 because a lot of things have happened over the last few months in AI, and I thought it was important to update this conversation. AI and AI ethics is my own area of research. It's the area that I've published the most in, so I have a lot to say here. Previous versions of these lectures went a few hours longer than they probably should have, so I'm going to try to keep things as focused and efficient as possible, but I have a lot of things I want to talk about here, so I'm looking forward to it. The lesson plan for Lesson 12 is to start with a little bit of a discussion of the history of AI and history of computing, just to put some of this conversation in its historical context and give a little bit of perspective on what the recent developments in AI really amount to. I also want to say just a few words about machine learning, what it means to say that machines are learning, what sense in which they're learning, and what does that mean about what they can or cannot do. And then I also want to, the main focus of this lesson is to talk about AI ethics and some of the recent literature in AI ethics focused on things like algorithmic bias and fairness, transparency and accountability, explainability, and some other AI ethics issues. A lot of this is introduced in the readings for this week, so I have a documentary called Coded Bias, which is also on Netflix, if you have that. In this documentary is mostly going over Joy Buolamwini's Gender Shades paper and some of the conversations surrounding that from her and her colleagues. I also have a lecture from Emily Bender, who's one of the more vocal AI critics over the last few months and years. Bender has this lecture on resisting dehumanization in the age of AI that you might also find helpful in understanding the particular kind of risks that we're facing in the moment. And then there's this very well-known paper from Engwin et al. This is the ProPublica Machine Bias and Sentencing article that, when it came out in 2016, really clued everyone into how these issues are not sort of speculative science fiction issues, but that AI ethics really matters for people today. So in the Engwin article, they talk about the use of machine learning algorithms in criminal sentencing processes in the justice system today. So this is not science fiction. This is the real world. Then I have some optional papers. You can read the Gender Shades paper directly, or the stochastic parrots paper from Bender, both very well known in the AI ethics literature. There's also a lot of resources in these slides, some videos, a couple of demos, and some other reading material that you might find helpful in sort of getting a handle on what AI is and what's going on. But our real goal is to talk about the history. Let me go ahead and get my head out of the frame. Our real goal in this lesson is to talk about the history of AI and to put the current developments in their proper context. I've seen some people talk about the current boom in AI as the AI spring. And one of the things that's nice is that we can date the start of the AI spring pretty precisely to when Jeff Hinton beat ImageNet in 2012. ImageNet is an image identification benchmarking test that until 2012 no one had really successfully beat it, but Hinton used some deep convolutional neural networks, which is one of the standard technologies being used today, in order to beat ImageNet. I will say more about how ImageNet works a little bit later, but it was after beating ImageNet that the AI boom sort of really gets going. The year after Hinton beat ImageNet, he gets hired by Google to lead their AI research, and Yann LeCun, who's the guy who developed convolutional neural networks, was hired by Facebook that same year in order to head Facebook's AI division. And a lot of investments started happening around that time. And in particular, one of the very first consumer products that used artificial intelligence or machine learning actually came to the market, which was predictive text. Everyone knows predictive text on your phone. It's the suggestion of what the next word should be. This was technology that was introduced in 2013 using Hinton's understanding of these neural networks. It was a very successful and popular product. Everyone loves predictive texts. But it was also the first time that machine learning had really found its way into a consumer product. And once people saw that was happening, then everyone was off to the races, and huge amounts of money started getting invested. There were a bunch of early successes, like with AlphaGo and AlphaZero and so on. But a lot of that early investment is only now starting to really bear fruit in ways that the public is appreciating in services like ChatGPT, which was released last November, and all the image generating software, Midjourney, and so on. All that stuff is just starting to come out and starting to cause a lot of controversy. And I want to talk a little bit about that controversy. But I want to start by giving a little bit of perspective. And the first thing to say is that one of the reasons we call the current boom AI Spring is because prior to this, we were in a period that was widely known as the AI Winter. AI Winter was a period of about 20 to 40 years, depending on how you count them, where there just wasn't a lot of development in AI. There were a few people doing a little bit of research, but for the most part, a lot of the funding dried up because a lot of the more radical claims that the people in AI were making just didn't look like they were going to come to fruition. So part of what we want to do in this history lesson is sort of set up what happened in the AI winter, what caused it, and sort of what happened in order to give some context for what's happening now in the so-called AI spring. Okay, but I want to start really, really early on to a much older understanding of what computing is. Part of the point here is that we shouldn't be thinking about computation or computing technologies as something that's unique to the digital age, to the 21st century, but that, in fact, these computing technologies have been around for a very, very long time, are a deep part of human history. So on the screen here, I have an image of an abacus. Abacuses are also thousands of years old, and in fact, some of the earliest writings that we have from human beings of human civilization are things like receipts from selling a bunch of goats at the market, bookkeeping documents that show how much of what thing that people have and how much it was being traded for, and this sort of stuff. So this kind of mathematical bookkeeping is a deep part of human history. Again, the oldest documents that we have, the oldest written documents that we have, are some of these bookkeeping documents. These technologies are computing devices in the sense where computation is orderly operation. So it's tempting to think about computers the way that we think about our laptops or desktop computers or our cell phones as these electronic devices. But I think it's important to understand that computation is a much more fundamental thing that human beings have been dealing with for a very long time. And that the computation is really just orderly operation. That what it means to compute is to perform an operation in an orderly fashion so that you can keep track of your results very precisely. So think about doing like an arithmetic task, like adding two big numbers together, or subtracting two big numbers, or multiplying two big numbers together. And that's the sort of thing that you could use an abacus for. So the thing you see on the screen is an abacus from about 3,000 years ago, but abacuses were quite widely and commonly used all the way up until the middle of the 20th century. My own grandmother, who was born just after World War II in Tokyo, she learned in school how to use an abacus, and she was very quick at it. And I remember as a kid doing a demo with my grandmother where she had an abacus and I had an electronic calculator, and then someone would give us two big numbers to multiply or add together, and my grandmother would have the correct result on her abacus before I was done even typing the numbers into my calculator. So you can perform complex mathematical operations very quickly on an abacus. This is something that human beings have been doing for a very long time. And if we think about computation as performing these kinds of orderly operations, then an abacus is just a computing device. It's a computing device thousands of years before we had electricity, or we had devices using electricity, or this kind of thing. If computation is orderly operation, then you can think of an algorithm as a sequence of operations, or computations in order to get some result or in order to complete some task. So for instance, you might remember how to do long division from elementary school. There's a process when you divide two big numbers or one number into another number. There's this process that you do called long division. Every step in that process, the process itself is the algorithm. It's the long division algorithm, and the algorithm is just a sequence of steps that you perform in a certain way in order to get the correct result. And if you know the long division algorithm, then every time you execute that algorithm correctly, then you'll get the correct answer for some division problem. So the algorithm is the process, and the computation is each sort of step in that process, each operation being performed. Just a couple more sort of ancient computers to think about. The astrolabe is another computer. Part of the point here is that the kinds of operations that you can perform, maybe it's easiest to think about mathematical operations like adding or subtracting numbers or dividing or multiplying numbers. But the kind of basic computations you can perform is just anything that has a sort of orderly framework, and it doesn't have to be mathematics. So the astrolabe isn't performing arithmetic; it's performing astronomical calculations. So you can, for instance, point your ship in the right direction as you're navigating the globe. The astrolabe will let you calculate the correct longitude and latitude of where you are by lining it up with the stars that you see in the sky and knowing a little bit about astronomy. So in this case, you're not the computations are not arithmetic computations like adding two numbers together, but they're really geometrical and astronomical computations about figuring out your orientation relative to the stars and planets. Again, this is the kind of device that has been used for thousands of years, long before we had any modern computing technologies, or digital computing, or electronic digital computers. This is not an ancient computing device. This is maybe like an early modern computing device, but another example of a computer, just to get a flavor for this more broad definition of computation. Another example of an early computer is something like a pocket watch. Pocket watch is a highly sophisticated, technologically advanced machine whose job it is to perform certain operations in a very orderly way. In particular, it's the goal of the pocket watch is to tick by 1 second per second and to keep accurate time. And so you need all these little gears and springs in a pocket watch calibrated just so in order to keep accurate time. One of the important things with the pocket watch is that it was also very important for modern life, for participating in modern life. Maybe less so in the 1600s, but especially as industrialization started flourishing and more people were living in cities and dense urban environments required accurate timekeeping in order to know when a delivery was going to be made, or when a meeting, when the meeting was going to happen, or to catch your train. And having an accurate timekeeping device was sort of essential for navigating that complex urban world. And so the pocket watch is one of these examples of a highly sophisticated technological device, a computing device, that everyone was sort of required to keep in their pockets in order to participate in the public sphere. So that's sort of a precursor, a pre-electronic precursor of modern cell phones. One more historical example of pre-computing devices that shows how computation sort of matters in the history of technology long before we have electronics is the Jacquard loom. So you might have also learned about this in elementary school. The Jacquard loom is a loom. A loom is a weaving device. It makes fabrics out of threads. So you can put the threads together in a way that will generate these fabrics. We've had looms for a very long time. Pre-industrial era, looms have been around for quite a while. But in the industrial era, when we're making lots of looms, when we're making lots of fabric very quickly on these industrial scale looms, there's also a desire to have the fabrics be customized and personalized, or have different patterns in it in order to make them more attractive and valuable. And before the Jacquard loom, these sort of patterns would have to be woven into the fabrics by hand by adjusting the threads that you're putting at each stage of the weaving process. But what Jacquard figured out is a way of automating the pattern in the fabrics with these punch cards. So you have a normal loom here, but on top of the loom you have these punch cards going through, and the punch cards have holes in them, and the holes allow certain needles with certain threads through the holes, so that they can put the thread into the fabric pattern. And then it would block other needles from going through, so that those threads would not go into the fabric pattern. And if you set up the cards in the right sort of way, then you can control what pattern is being woven into the fabric. So it's an interesting automated technology here. But one of the reasons why it's fascinating is because if you know anything about early computing, early computers also used punch cards, like the sort of computers used in Hidden Figures. If you've seen that film about the early NASA computers, they have computers that they use these little punch cards. The punch cards also have holes in them, just like the Jacquard loom. But in the early computers, it wasn't to allow needles to go through with a certain thread, but instead it was to allow certain electrical signals to go through and block others. Right, so the punch cards were the early way of programming these early computers by adjusting their sort of electronic circuits with these punch cards, letting some signals through and blocking out other signals. And the inspiration for those early punch cards in computers was directly from the Jacquard loom. So part of the lesson here is that computing doesn't come out of nowhere. A lot of the motivation and a lot of the technological innovations and designs that allowed for the modern computing era was already in the technological sort of atmosphere. And it wasn't just like one person who came up with a brilliant idea. It was a lot of little technological incremental steps that all get eventually put together in the right sort of way to create the modern digital computer. So the earliest attempt at building something like a computer is Charles Babbage, who was sort of an eccentric inventor, and Babbage was really interested in industrial processes, and he wrote a book looking at a bunch of different industrial era factories in the early 1800s. He went all over Europe looking at these different factories and how they operated and what technologies they were using, what were the tricks that were making the factories successful. And he wrote a book about this, but one of the things he noticed as he was going around was that every factory, every industrial manufacturer needed to do precise computations. They had, if they were making large orders and keeping large inventories, then they had to monitor those inventories with accurate bookkeeping, which means doing a lot of mathematical operations. And doing mathematical operations wasn't easy. You'd have to hire people for this. I'm actually going to skip forward in my slide deck. In the pre-digital computer era, a computer was someone that you'd hire. Often it was a woman that you hired because computing was considered secretarial work or office work, and so that it was considered women's work. And you'd hire people as computers. So a computer was a job that a person had, where they would sit at a desk and add and subtract large numbers together in order to keep the books for some large organization. So the images on top are from Bletchley Park, which is where some of the code breaking was done during World War II. But the image on bottom is from Sears Roebuck, which was a catalog, a mailing catalog company. They would send you a catalog and you can order things, and they would send you those products through the mail. So Sears Roebuck was in some ways the Amazon delivery service of the early 20th century, late 1800s, early 1900s. And in order to run a sophisticated mail-in catalog operation, you needed to perform a bunch of computations. So Sears Roebuck literally hired warehouses full of women in order to do a lot of the computational work that made their company viable. So it was, before we had digital computers, you were hiring people. But part of the challenge is that people aren't always perfectly accurate. Even the best mathematicians will make mistakes on their computations, and those mistakes could have big consequences in the operation of the business. And so one of the things that one of the ideas that Charles Babbage had is if we could automate the computations, if we could build a machine that performed the computations for us, then we wouldn't have to hire people to do that job, and we wouldn't make so many mistakes. So Babbage designed a couple of different machines, the analytical engine and then the difference engine. Babbage designed these machines in order to perform automatic computations. Let me just show this real quick. Here we go. So this is this is Babbage's difference engine. Babbage never actually built this machine himself, but you can see that it's a hand cranked machine. There's no electronics here. It's all just a bunch of gears, but the gears are controlling these columns. Moving forward a little bit, these little columns that spin around and latch on to the next column. And you can configure it in such a way to perform mathematical operations similar to a abacus, where the latch would hit the next column in order to signify a carry, and then by rotating, by cranking the handle and rotating all these gears, and having the gears configured in just the right way, you can have it perform some complicated mathematical operation. Just zooming forward a little bit here, you can see that not only did it perform the operation, but it actually printed out the operation on a piece of paper, so that from input to output, the whole thing was controlled by the machine, and there was no room for human error. So cool device. Like I said, Babbage never actually built this machine. He he did build a part of the machine. He built like he built like a half of one of these columns, and the point of building the piece of the machine was just to demonstrate how it worked in order to raise funding. So Babbage spent quite a lot of his life going around to politicians and wealthy businessmen in England in order to get someone to fund his automated computing machine, his difference engine. And he never got any takers. No one could see the point of investing a lot of money into this unproven, untested technology that was very expensive and very intricate, when you could just hire people to do that same job for relatively cheap. Performing mathematical computational work was not high-skilled. It was not considered high-skilled labor. It was considered sort of low-skilled labor. You just needed a high school degree in order to know how to do a high school diploma in order to know how to do the arithmetic operations. So Babbage never got his difference engine funded. He wanted it funded, but no one saw the point of investing in it. After Babbage died, some scholars took his designs and using machining techniques of his day, tried to implement those designs in actual hardware, and it worked. So the machine that you saw is in a museum somewhere, but it works just the way that Babbage envisioned. One of the things this means is that we could have had computing technology about 100 years before we actually did. And maybe history would have turned out very differently if Babbage was able to get his machines funded. It would have meant that we would have had general purpose computing technology before we had electricity. But that's not the way things turned out. One more just note about Babbage. One of the things, when Babbage was going around trying to raise funding for his machines, he would throw these parties to try to raise awareness and get people talking about the possibilities. At one of these parties, Babbage runs into Ada Lovelace. Ada Lovelace was the daughter of Lord Byron, if you know from poetry. Lovelace had a strong interest in mathematics, and had a bunch of great mathematical tutors. And then when Lovelace saw Babbage's designs and saw the little component that he had made as a demo, Lovelace was one of the few people who really understood what Babbage was doing. One of the few people who really appreciated the mathematical motivation for building such a machine, and also what that machine could do. So after meeting Babbage, Lovelace and Babbage had a correspondence. They exchanged letters, and Lovelace talks in part about the different ways you can configure the machine, the analytical engine, the different ways you can configure the analytical engine to perform certain kinds of mathematical operations. It was by writing about the way to configure the machine that Lovelace comes to be known as the world's first computer programmer. There's a Lovelace Day, I think it's in August, where computer science celebrates Lovelace and celebrates women in computing. And it's because Lovelace was designing programs for a computer that hadn't even been built yet. It was just that Lovelace understood conceptually what the machine was designed to do, so she could build little configurations of it to perform certain kinds of mathematical operations. Lovelace wasn't only thinking about mathematics, she was also imagining more sophisticated things you could do with these machines. For instance, she noticed that you could, instead of just performing some arithmetic operation, you can associate each of the numbers with a musical note, and then you can build algorithms that generate sequences of musical notes in interesting ways. In imagining this kind of thing, Lovelace is also credited with one of the first ideas of algorithmic music or computer-generated music, where she's imagining again this machine that hadn't been built as being used for the creation of music. And we're going to come back to this in a second, because Lovelace is also going to have some of the important objections to artificial intelligence, but we should move on. Babbage doesn't get to build his machine in the early 1800s, and we really have to wait for Turing to come around 100 years later to build to map out what a universal computer would be. This is the so-called Turing machine. I won't get into the details here. But the important thing about Turing machine is a mathematical framework for talking about an automated computing device. So Turing doesn't actually build any physical machine that's the Turing machine. He really just describes it as sort of a formalism in his mathematical papers. But that said, it's important for Turing that the machine that he's describing is a machine in the sense that you can build it from mechanical parts. That it's not imagining some mysterious computing mind, but that you can build just a normal machine that's doing some straightforward mechanical operations, but that the machine can also perform mathematical and computational operations. So in Turing's machine, it's sort of based on the way that film projectors work. So like you have a film, and if we're watching a movie, then each one of the frames here is a different frame of the film, and they all sort of move. And if you spin them really fast by a light, then it looks like the image is moving. But in Turing's machine, instead of each one of these frames being an image, instead it's holding a bit of data, so a 1 or a 0, some numerical value. And what the Turing machine can do is it can write some numerical value onto the tape. It can also read what numerical value is on the tape in each one of these cells. And it can also move back and forth, right? This is the head of the tape. The head of the machine moves back and forth across the tape. So not just in one direction the way that it does in a movie, but the head can move back and forth across the tape in order to read and write from the tape in order to perform its operations. The read-write head and the tape are all mechanical parts that you can buy off the shelf. It works the same way that a movie projector does. The one interesting thing is the program. This is the third part of the Turing machine. And the program tells the read-write head how to move back and forth across the tape in order to perform its operations. So you can write different kinds of programs that perform different kinds of operations on the data on the tape. One of the things that Turing realizes is that the program itself can be encoded into values that you put on the tape. And so in some sense, the program doesn't need to be a separate part of the tape. It just needs to be data that's on the tape itself. And so you really only need the memory and the read-write head, and then you have everything that you need in order to perform these sophisticated computations. And there's a lot more here to be said about Turing's machine, but what Turing really gives us is this mathematical framework for what computation is, and what it can and cannot do, and how to build machines that could perform computations. So this is like someone actually built a Turing machine that works the way that Turing describes it, but Turing didn't actually build a machine like this. Turing just wanted a machine that can perform general computations. But the framework that Turing describes, the so-called Turing machine, its big mathematical value is that it allows for a discussion not just of performing some specific computation, some specific orderly operation, but it provides a framework for thinking about universal computation. In other words, a machine that can perform any computation you want, or a machine that can execute any computable function. And this forms the groundwork for computing machines today. The computer in your phone or the computer in your laptop is a universal computer in the sense that it can perform any computable function, that anything that can be computed by a universal computer. And almost every example of a computer that you know about, like your phone and your laptop, are examples of universal computers in this sense. This is why your computer is able to emulate, for instance, an old NES gaming system or like a PlayStation 1. You can emulate those on your computer because your computer's, in principle, capable of performing any computation, and the PlayStation is also performing some computation, and so your computer can also perform that same computation. Okay, so Turing didn't actually build one of those machines. Turing spent a lot of time building special purpose machines, like a machine to decrypt the Enigma code, which was the cryptographic device that the Nazis used in World War II. Turing defeated the Enigma device with this Bomba machine. He didn't design the Bomba machine, but he built a working version of it. There's a working version of this at the History of Computing Museum in the UK, where you can actually see the little spindles here are on the front of the machine, and this is the back of the machine. And the little nozzles are spraying out oil because this whole thing is it's a mechanical device that works a lot like a pocket watch or a clock, where it's a bunch of gears rotating against other gears to see if it would all work. And the Bomba machine was able to decrypt the cryptography that the Germans were using in World War II. and it was sort of important for the anti-war effort. But Turing's machine probably did less for the anti-war effort than the human computers that were hired as code breakers at Bletchley Park, where Turing was doing this work. It was the human computers that found a lot of the hints that were being used on the machines in order to decrypt the devices. So a lot of credit goes to the human computers that were doing this this work. And it wasn't until near where Turing dies that we actually have... Turing died in 1954, I believe. And the first actual consumer-grade computers start coming out in the very early 50s. UNIVAC is one of the first computers to be sold commercially. And UNIVAC was also used in some important things in the early 50s. Like it helped with the tabulation of the 1950 census. It made election predictions for the 1954 presidential election. And so in this way, the UNIVAC started to become part of popular consciousness. And shortly after we had available these digital computers for consumers, there was also an interest in AI. So the very first AI conference, like we can date the beginning of AI or at least beginning of the modern era of AI, pretty precisely. Also to this 1956 conference at Dartmouth. All of the important early researchers in AI were at this conference, and the goal of the conference was to find if every aspect of learning or every other feature of intelligence can be so precisely described that a machine can be made to simulate it. In other words, can machines do the things that we think of when we think of intelligent tasks, such as learning? So this was an early effort in AI. Some of the early thinking in AI comes from people who attended this conference, and those people go on to produce some of the early successes or sort of notable milestones in early AI development. So this is the what I'm calling the golden age of AI. Starts with that Dartmouth conference and goes till maybe the mid-70s. And a lot of the famous early examples of AI come out of this era, like Eliza. Eliza is the first chatbot. You can go online and talk to Eliza. There's a bunch of simulations of the original software online. Eliza was a chatbot. You ask it questions in English, and it gives you responses in English. The kinds of responses that Eliza gives is not very sophisticated, and especially if you've talked to any chatbot in the last 10 years, Eliza looks pretty simple. Basically, all Eliza does is just take what you tell Eliza and then just turns it into a question and spits it right back at you. So you say, you're just talking nonsense. And then Eliza says, well, what makes you believe that I am just talking nonsense? And it looks like a reasonable question at first. You might try to answer it, but eventually you see that Eliza's not really asking any questions at all. It's just phrasing questions in a way that's compelling and that sort of makes people want to respond. But the early researchers who built Eliza thought it was convincing enough to spend hours talking to it, to come out of sessions talking to Eliza feeling like you'd gone through some therapeutic catharsis. And a lot of this was just projection from the users, but nevertheless, Eliza was an example where you were, in some sense, talking to a bot. Another early example of early success in AI from around this period is Shrdlu, which was like a general-purpose reasoner. I forget what the acronym SHRDLU stands for, but Shrdlu was a general-purpose reasoner. It couldn't reason about the real world, but it could reason about this little toy world. And again, you could interface with it in natural language. You could say things like pick up the red block or pick up the blue block. In the Shrdlu demo, there was the different blocks had colors, and you can't really see it in this diagram. But this little toy world had little blocks in it. Some of the blocks were cubes, and some of the blocks were like pyramids. And you could tell it to do things in this world, and it would understand for the most part what you were asking it to do. And it also understood what it could or couldn't do. So like if you asked it to put the red block on this pyramid, it would say it couldn't do that because the blocks can't stand on pyramids, because pyramids have a little point on it, and it means the block will fall over. And instead of rendering what would happen if the block fell over, Shrdlu just says, I can't put the block on the pyramid. Or like if you ask it to pick up this block where the pyramid's on top of it, it'll say I can't pick it up because something else is on top of it. So it could do this kind of very simplistic reasoning about this oversimplified toy world, but it could do it in natural language, and people were talking about Shrdlu as an example of an early general-purpose reasoner. In this early era of AI, There was also attempts at building learning machines, the most famous of which is a perceptron. Perceptrons are still used in some applications today, but perceptron was like the first attempt at building a machine learning model, where you're not just programming the machine for what it should do, but you're actually getting it to learn. The perceptron is a very simple system where you have some inputs, and you want it to give you some output. And the way that you do this is you multiply each input by some weight, right? So if you have n inputs and you have n weights, they're each being multiplied by, and then you just add all those multiplications together, right? So I1 times W1 plus I2 times W2 plus I3 times W3 for each one of the inputs and their weights. Multiply them together and then add everything up, and that gives you your output. This is how the perceptron works. Again, it has some application. The way that it's a learning machine is that you can adjust the weights on the perceptron in order to fine-tune the outputs that you want. Right? So you give it some inputs, and then you make adjustments on the weights in order to fine-tune the output. And the output would get fed back into the input, and then you can keep adjusting the weights, and you can sort of keep adjusting the model to fit whatever task you're doing. And the perceptron was used for tasks like classification. In fact, one of the most general applications of machine learning models is for classification tasks, like sorting a big data set into the different components of the data. So here, imagine a data set with a bunch of dogs and cats, where they're all have some attributes like their size. And so the idea here is that dogs are generally bigger than cats. This isn't always the case, but dogs are generally bigger than the cats. So you can imagine that the classification task here is just to draw some line in the data set that puts all the dogs on one side and all the cats on the other side. So if it's just one dog, if the data set only consists of one dog and one cat, then drawing a line might be trivial. But as we add more data points, drawing a line that puts all the dogs on one side and all the cats on the other becomes a little more tricky. And so basically what you can think of the perceptron as doing is adjusting the slope of the line in some data set in order to properly classify the members of that set. So as you're changing the weights, you're also basically changing the slope of this line. So this sort of works. Thinking about the perceptron as changing the slope of the line also shows how it's used in modern contexts. When I was in grad school, I worked on a project where we were training a flight simulator. We were training an airplane to fly in a flight simulator in Microsoft Flight Simulator. And we did it with a perceptron, and you can imagine the perceptron as just being this line where the line is equal to the slope of the wings on the plane. And so what we want the perceptron to do is make slight adjustments to how level the plane is in order to steer and turn and keep itself balanced. And so the perceptron here is again it's making small adjustments to the weights in order to keep the plane balanced, in order to keep the plane in the sky. So this is the kind of thing that perceptrons get used for even today. But these have been around for quite a long time. There's a problem with these perceptrons, though, and the problem is that they can't do nonlinear classification. So the only kind of data sets that a perceptron can classify are data sets that can be classified with just a straight line, with just the slope of the line. You can adjust the slope of the line, but you can't make the line any more complicated. So it only works on data sets where the data is accurately or is usefully classified with just some straight line. And the problem is that most data sets are not like this. Most data sets are not linearly classifiable. Most interesting data sets from the real world have all sorts of weird nonlinearities and complications that make it much more complicated than just drawing a straight line. And people realized this pretty early on. There's a famous famous book in the 70s, I want to say, or maybe it was in the late 60s. It was by Marvin Minsky. It's called The Perceptron, where they talk about this limitation of the perceptron. The perceptron really, it can't handle nonlinear classification tasks. In fact, there are even some more basic logical operations, like exclusive OR, that you cannot train a perceptron to do. So it was clear pretty early on that the research agenda of the perceptron, or what the perceptron was trying to do and build general learning machines, was just not going to come to fruition. And also, like ELIZA and Shirtaloo clearly had some pretty significant limitations on their capabilities, and it wasn't exactly clear how to make them more sophisticated in the short term, especially because computing technologies were still just being introduced, and they were still very expensive and difficult to get your hands on, even into the 70s. Nevertheless, despite the clear limitations of the field and the limited success of some of the early demos of AI, there was a lot of hype in the field as well. There was a lot of optimism about what would shortly happen, that very quickly we'll have machines that are doing far more sophisticated things. So these are some of the big names in AI: Herbert Simon, Marvin Minsky. Both of them were at that Dartmouth conference, and both of them spent the next 20 years going into public venues and saying talking about all the incredible things these machines will do in the very near term. So Herbert Simon in 1965 says that within 20 years we'll have machines capable of doing the work of any man. Marvin Minsky says in 1970 in Life magazine, a popular magazine, Marvin Minsky says that from 3 to 8 years we'll have a machine with general intelligence of the average human being. And I don't have to tell you all, born decades after these claims, that these claims are just not true. And they way overstate the capacity of these machines, and they also way overstate the timeline in which the machines are going to develop. Maybe this was compelling in the late 50s and early 60s, when these computing technologies were just coming around, but it very quickly became clear that the AI as a field was overselling the technologies that it was producing, and that it was making predictions that were just impossible to consider realistic. And so people increasingly started thinking of AI as a field full of crackpots, and it started getting a bad reputation for making these kinds of wildly optimistic claims. That was kind of bad, but it really became a crisis for AI when this kind of hit to the reputation started making an impact on funding. So in 1973, the Lighthill Report was a report to the British government, British military, on what's happening in AI and where the future is in AI. And in the Lighthill Report, Lighthill says that, or the people who wrote the report say that it was that the claims being made by AI practitioners are way overhyped, and it's probably not going to be that their predictions are probably not going to be accurate, and that they're expecting a lot more than is realistic from their machines. So in the Lighthill Report, the recommendation is that the British government stop funding AI research, that the funds are not going to be used appropriately, but they're going to be used in these ways that are overhyped and not realistic. So the British government follows the Lighthill Report. In 1973, they cut off funding to any AI project. The very next year, DARPA, which is the U.S. military research and development wing, DARPA also cuts funding to AI projects. And now there's no more money in AI, and so everyone leaves the field. Very quickly, by the late 70s, if you're still working in AI, if you're still saying that you work in AI, you're kind of a laughingstock. People don't take you seriously anymore. And the people who were formerly working in AI either switched jobs or switched job titles, so that it seems like they're not doing the same thing. A lot of people who were working in AI changed their names, changed their job title to something about expert systems. So there's a big field that develops called expert systems, which is really just a lot of the stuff that they used to call AI, but they changed the name because no one's funding AI anymore. And this is how the AI winter starts. So from about 1973 or 1974, and for the next 20 or 30 or 40 years, there's just not a lot of money in AI, and so there's not a lot of people working in the field, and so there's not a lot of progress being made. It's in this time period that also some of the big criticisms of AI start to become popularized. Dreyfus writes his What Computers Can't Do in 1990. Dreyfus publishes an update, What Computers Still Can't Do. In 1980, Searle publishes his Minds, Brains, Computers, which is where he gives the Chinese room argument. These are some of the more popular, even today, popular arguments against the possibility of thinking machines or artificial intelligence. And these anti-AI arguments become popular in the AI winter. In other words, they're sort of kicking AI when it's down. I emphasize the AI winter here partly because there are these persistent myths still in AI and in technology, in computing technologies, that technological growth is inevitable. A lot of these myths are based on Moore's law. Moore just died a couple of weeks ago, maybe even last week. But Moore was not a theoretical computer scientist. He was not a technologist, sort of a techno-futurist. Moore was he was an engineer, but he worked at Intel. He was one of the managers at Intel, and Moore's Law comes out of them trying to build a roadmap for what happens in the industry over the next couple of decades. They want to know what kind of technologies we can expect, so they can allocate their resources and put their emphasis where it's going to be best used in the industry. So Moore worked for Intel. He helped to develop the tick-tock model that Intel used for releasing their chips for several decades. But what Moore noticed was that, especially very early on, that as new computing chips were coming out, they tended to have more transistors, and Moore noticed when you plotted the number of transistors on these chips over time, you got an exponential growth curve. This is on a logarithmic scale, so when you see a straight line on a logarithmic scale, that means exponential growth. And so Moore's law is not really a law. It's just noticing this pattern that transistors, the number of transistors on a chip double about every 18 months. I think this was the original formulation from Moore. And so Intel built a tick-tock model, thinking, well, okay, if chips are doubling in capacity every 18 months, then this is how we're going to start selling them. The idea is that every 18 months or 2 years or so, you put out a tick, and then 2 years after that, you put out a tock. So the tick was a new chip with a new set of transistors, new chip design, can do all sorts of new things with more transistors than the last generation. And then the tock was the optimization of that chip, right? So you put out a new chip with a bunch of transistors, and then after using it for a couple of years, you figure out the strengths and weaknesses of that chip, and then you optimize it and make a better version of that chip, and that's the tock. And then after a year or two, you put out the new chip with new number of transistors, and then you optimize it again after that. And this sort of tick-tock model drove Intel's chip release schedule for several decades, all the way up through into the 90s. And so it was really important framework for the industrial production of these technologies. But it's been used, Moore's law and this idea of exponential growth, it's been used to justify a lot of more unhinged theories about technological growth and development. In particular, there's this still popular idea of the singularity. It became less popular for a while, but once ChatGPT came out, a lot of people started jumping on the singularity bus again. And the idea of this technological singularity is that, okay, so if we accept that Moore's law shows that technological growth doubles every 18 months or 2 years or so, and that it's on this exponential growth, well, computing technology grows exponentially, but human brains are not growing exponentially, or they're growing at least in a much slower scale. Like your brain anatomically is more or less the same as human brains from 30,000 years ago or 50,000 years ago. So human brains individually don't grow very fast. Evolutionary time is very slow, but computing technology seems to be growing exponentially fast. And the idea is that if brains are more or less constant computing power and computing chips are exponentially growing, then there's going to be some point where the computing chips are faster or more powerful than human brains. And not just individual human brains, but the combined brain power of all humans. And the idea is that if technology is just growing at this exponential rate, then it's just inevitable that it'll surpass human intelligence, both individually and collectively. And this is the idea of a singularity. The singularity is this point where the computers pass human ability. And the idea is that this might be a point where we should be worried about, because if computers are more powerful than us, then maybe they will do things that are not in our interest, that computers will take over the world, this sort of thing. And this view is popular, and a lot of people believe it, especially a lot of my students at NJIT will talk in these terms about a technological singularity, or about AGI, which are the machines, the artificial general intelligences that exist after the singularity. And it's important to appreciate that this is just not true, that the idea of a technological singularity, it's really this sort of science fiction myth that's become very popular, but it really has not much credibility or basis in reality or in critical thinking. So it's one thing to say right off the bat is that Moore's law is not, it's not a law of nature, for sure. It's the law of the industry, maybe, but it's also not inevitable. So over the last decade or so, Moore's law has basically run out of steam in the sense that we're not able to make our transistors any smaller or pack more of them on a chip in the way that we were able to do, throughout most of the 20th century, into about the late 90s. But after that, we started to run into limitations on how densely we can pack the transistors, how small we can make them. And for the last more than a decade, we're not seeing the same kind of exponential growth. So like my laptop today is not twice as powerful as my laptop 2 years ago, at least in computing terms. There are some advances. The technology, the point is not that technology doesn't advance at all, but just that the technology is not advancing in its computational capacity. So my laptop is now more power efficient. It has longer battery life. It has a better screen. This kind of stuff. So there are advances, but those advances are not about its fundamental computational power. And in terms of computational power, there's been this sort of plateau in processing units. The solution to that has been just putting a whole bunch of processing units having multiple cores. And this is how GPUs run. But even there, we're running into physical limits on how densely we can pack transistors. So Moore's law is dead, which means this exponential growth curve doesn't go on forever. That's a big reason to think the singularity is not a real thing that's going to happen. But there's even better reasons. One thing is that having more transistors on a chip doesn't mean that it's necessarily more intelligent. It matters what those transistors are doing. It matters what the software is that they're controlling those transistors. And Moore's law doesn't track anything like that, right? So there's not a strong reason to think that intellectual capacities or the capacities of machines to do intelligent tasks is growing at the same exponential rate. Rather, it seems like sort of bursty. Like when ChatGPT releases, then we can get machines to do a bunch of these tasks that they weren't able to do before. But then we sort of figure out what those applications are, and then we're back into a period of stagnation until we come to the next technological breakthrough. So just counting transistors in the chip is not sufficient for making these kinds of predictions into the future. But maybe the best evidence against singularity theory is the AI winter that we just talked about. Right, there was a period of 40 years where AI development just stagnated, and it wasn't because there was something wrong with technology. There was technological development all over the place. What happened was a change in our social attitudes towards AI. Right, people stopped funding it. They stopped taking its leaders as credible. Right, there was these sort of social changes. In early computing, people realized that there were more opportunities working in things outside of AI than on AI, and so the field just bottoms out and stagnates for 40 years. Part of the problem here is that some of the ideas that people wanted to explore with AI just weren't possible on those old computers that weren't computing fast enough to make those kinds of tests reasonable. But that just reemphasizes the point that this thing isn't just an inevitable growth of technology. The technology doesn't just grow inevitably. It's not a law of nature. It's really a function and entirely dependent on human social attitudes, our political and economic situation, whether we have the funds to invest in these technologies, whether we think we'll get anything out of that investment, whether there are better things that we can be investing in. Right? All of these issues matter to how technology changes. These are dynamics that are already present in human societies, political and economic dynamics already present in human societies that have a huge influence over how technology makes progress. And when social attitudes change, that progress can also change. Right? So the AI winter is just proof positive of that sort of thing. I should also say that a lot of the singularity theory is bound up with these sort of end-of-the-world ideas, sort of so-called eschatological thinking. Eschatological thinking is about the end of the world and like the big risks of the end of the world. So a lot of singularity theory is caught up with the idea that computers are going to take over the world, or computers are going to represent some existential threat to humanity. And this kind of thinking, when someone tells you that the world's about to end, you should probably be very skeptical. They're probably overstating their case. Maybe this isn't always a good rule of thumb, because maybe there are legitimate end of the world worries when we're talking about climate change. Not end of the world like robots taking over the world, but end of the world as we know it, like our current models of economic and political organization, won't sustain the next 100 years. because of changes to the climate. You might also think that there will be significant changes in our political, social, and economic situation because of AI, but that seems less dire when you consider the facts that we get from environmental science, about ecological collapse and species going extinct, and so on. Like you might think that the threat from a changing climate actually does represent some direct threat to the next couple of generations of human beings, whereas a singularity might be something that our far future humans have to worry about, but don't represent the same kind of immediate threat that we're dealing with climate change or nuclear weapons and other sorts of risks that we face today. So I just want to generally encourage you to not believe the hype around singularity theory and to subject your thinking around AI to some more credible claims. Okay, so I want to go back to the history of AI and into the modern machine learning context. But just one more time, when AI winter starts, this is also when a lot of the anti-AI philosophical arguments start to gain currency. So like Dreyfus's "What Computers Can't Do" and Searle's Chinese Room argument. But maybe one of the strongest arguments against AI comes from Lovelace herself. Remember, Lovelace is thinking about algorithmically generated music, but Lovelace makes clear that the machines are not doing this creative expression on their own. It's not really a creative expression of the machine at all. Lovelace argues instead that the machine is just doing what we told it to do. Lovelace argues that the analytical engine has no pretensions to originate anything. It can only do what we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths. Its province is to assist us to making available what we are already acquainted with. Right. So the only reason that we can get the analytical engine to do a math problem is because we already know how to do those math problems, and we're just telling it what we already know. Similarly, with computer-generated music, we can get the machine to generate music, but that's because we already know how those notes work and how to associate them, so that the machine can produce music that is already sort of suited to our tastes. But that's because we're the ones who told the machine what to do and how to do it. This is a very popular argument, I think, still today, that the machines are not doing anything on their own; they're doing what we told them to do. And this is an argument that Turing also deals with directly. So in the 1950s, remember, Turing's the guy who develops the framework of the Turing machine, of the universal computer. And in the 1950s, Turing writes a paper called Computing Machinery Intelligence, where he talks about whether or not these machines are intelligent. And this is where Turing gives his famous Turing test. He calls it the imitation game. But the idea is that this is supposed to be a test to determine whether machines can think. And there's so much to say about this, and I'm not going to be able to say even a little bit of what I want to. I wrote my dissertation on Turing and Turing's tests, so I have a lot to say here. But Turing's test, the idea here is that you can imagine some interrogator who's C in this image. The interrogator is talking to a computer and is also talking to a person. And the question is, can the interrogator tell the difference between the computer and the person? Talking maybe not with voice, but with written text, so that way you're not judging just how well the computer can synthesize speech, but really about whether it can engage in a coherent and meaningful conversation. And so, in the Turing test, the judge asks questions to someone that might be a computer, might be a human, and then sees the responses and talks for about 5 minutes. And then the judge has to make a determination. Am I talking to a computer or am I talking to a human? And if the computer can fool the judge into thinking that it's a person, thinking that it's a human being, then the computer is said to pass the test. The computer passes the test because it fooled a human judge that its behavior is indistinguishable from another human, that a human could not tell the computer's performances apart from any other human being. We can talk about whether this test is any good or not, but Turing proposes this test, and he gives some arguments in its favor. He considers some objections to it. But one of the strong objections that he considers is Lovelace's objection, that the machine is only doing what we tell it to do. Right. So what Lovelace would say is like, okay, well, maybe the computer can produce some convincing text, but it's only producing that convincing text. It's only producing that convincing text because we told it how to do it. We programmed it in such a way that it's producing text that we're telling it to produce, and so no wonder it's convincing, because we're the ones who programmed that machine. So Turing worries that his proposed test doesn't actually get around the Lovelace objection, and Turing in the paper considers a lot of responses to Lovelace. One response that Turing gives is that sometimes machines surprise us, that I don't always anticipate everything the machine's going to do. Even when I program it, the machine sometimes does things that I don't anticipate. But Turing doesn't think this response is any good, so he gives another response, and this is where we get the idea of a learning machine. So the origin of this idea of a machine that learns is in Turing's response to Lovelace. Lovelace says machines only do what we tell it to do, and what Turing says is, well, the way that you get a machine to do something other than just what we told it to do, right? The way that you respond to Lovelace's objection is by building a machine that learns. And if a machine can learn, Turing argues, then it's not just doing what we told it to do, but it's also doing what it learned to do, right? So being able to learn means that the machine is not constrained just by its programming. This is Turing's argument. Now, Turing didn't have learning machines in his day. Maybe the perceptron comes around shortly thereafter. But really, for most of the 20th century, most computing programs work in a way where everything has to be explicitly coded. This is sometimes called good old-fashioned AI or GoFi. GoFi, good old-fashioned AI, is where you program a machine to do some specific set of tasks in a way that you program in advance. Right, so these early machines are programmed with conditional programming languages, where if this condition holds, then you do this, and if this condition holds, then you do that, and if this condition holds, you do that. And you just tell the machine what to do in all these different conditions. Right, so everything the machine does has to be explicitly coded in advance. All the instructions have to be coded ahead of time by human experts who know what the machine's supposed to do in all these situations. This is how good old-fashioned AI worked. A lot of the AI developments that we've already looked at, like ELIZA and Shirtaloo, are examples of this sort of good old-fashioned AI. Expert systems are all examples of GoFi. And one of the problems is that GoFi is really hard because you have to know exactly what the machine's going to do. And in any complicated task environment, it's really hard to anticipate every eventuality or every condition that has to be accounted for. And so just making a sophisticated GoFi machine is very difficult. But this starts to get replaced starting in the late 90s and into the present day with sometimes called NFI, newfangled AI, just to be the opposition of GoFi. But newfangled AI is machine learning, where you're not coding every explicit instruction, you're not telling the machine what to do in every step, but instead you're giving the machine the capacity to learn, so that the machine learns what to do in those steps, and you don't have to tell it in advance. And so this is the scenario that we're in now. This is the paradigm that we're in now, is this machine learning paradigm, where the machine is not told what to do at every step, right? So Lovelace's objection doesn't apply. But instead, the machine is given a learning framework and given a whole bunch of training data in order so that it can learn the rules to apply on its own. So this is machine learning, sometimes called connectionist networks or neural networks or newfangled AI. And newfangled AI, from the perceptron all the way to the present day, is these are called neural networks, and the idea here is on an analogy with brains, the way that brains learn, right? So your brain is made up of a bunch of neurons, and the neurons are basically little electronic triggers. So the idea is that a single neuron is connected up to a bunch of other neurons that is dendrites. So there's a bunch of other, imagine a bunch of other neurons here, and those neurons end in a connection with the dendrites of this neuron. And so this neuron is going to be connected to a bunch of other neurons on its dendrites. And then when those other neurons fire, some of that firing gets transferred as a small electrical charge to this neuron. And so as the neurons around it fire, as the neurons around it fire, this neuron starts to build up an electrical charge. And eventually that electrical charge hits some threshold where the neuron fires, and by firing it sends its electrical signal, the electricity that's built, down the axon, so that it can so that it can send that signal to the neurons that it's touching at its axon terminals. This is a way oversimplified model of what the neurons are doing. For one thing, they're not really touching each other, but the neuron, the connection between the neurons, one neuron's axon terminals and the dendrites of another neuron. There's a little gap. It's called the synapse. The synapse is where the neurons don't actually touch, but they just get really close to each other. And then when one of the neurons fires, that firing results in releasing a bunch of chemicals into the synapse, and those chemicals are picked up by the other neuron. And then the other neuron uses those chemicals to build up its own charge and eventually fire itself. So again, this is a way oversimplified model of what individual neurons are doing. But part of the idea here is that the neuron itself is not where all the sophisticated computation is happening. The neuron itself is just building a charge and then discharging that charge. What matters is not what the neuron itself is doing so much as the network connections that it has to all the other neurons. In other words, the intelligence happens not in individual neurons, but it happens in networks of neurons, how those neurons are all connected up and networked up, and how they fire in relation to each other, right? So individual neurons are fairly dumb, and you get intelligence from networks of neurons in these coordinated operations. Again, that's still a way oversimplified model, but this is the inspiration for building artificial neural networks, which are the machine learning models today. In artificial neural networks, you have basically the same structure where every individual node in the network is fairly dumb. It's not doing very much sophisticated on its own, and where all the intelligent behavior comes out is how these neurons are connected together. What operations are they performing as a network of activity? We saw the early version of this with the perceptron. Perceptron was a very early machine learning model. And again, remember, the perceptron fails because it can't do nonlinear tasks. It can't do tasks that require classifying nonlinear data. One of the things that brings us out of the AI winter is that people figured out what the problem with the perceptron was. In particular, Rumelhart in a series of papers in the mid-1980s, especially Rumelhart and McClellan in 1985, Rumelhart figures out that what is missing from the perceptron is additional layers that allow us to do more sophisticated tasks. So in the perceptron, you just had the input layer multiplied by some weight going directly to the output layer. But what Rumelhart figured out is that if we add additional layers between the input and the output, these so-called hidden layers, and they're hidden just in the sense that they're between input and output. If we add additional layers, hidden layers, then we can get a machine to learn more sophisticated tasks, including nonlinear tasks. In fact, it's proved around this time that if you get an appropriately trained artificial neural network, it's capable of becoming a universal computer. In other words, it can do anything that any Turing machine can do. And any computer, any universal Turing machine can do any computable function. And so if a neural network can become a universal Turing machine, then in principle, a neural network can also compute any computable function. So we figured out a way of making these neural networks generalizable to have them work on any task. And this is where the first seeds of the AI spring start to be developed. So just really quickly about these neural networks. So again, we're giving inputs, and those inputs are weighted. But here, again, it's different from the perceptron because those weights are not just going directly to the output layer, but those weights are going to input layers, these hidden layers. And sometimes you can have several hidden layers, and these hidden layers can be very long, so you have lots and lots of nodes. When people say deep learning, they just mean a neural network with lots and lots of nodes and lots and lots of layers. To give you some sense of how big the neural networks are getting today, GPT-3, GPT-4 is the newest model, but we don't know how GPT-4 was constructed because they haven't told us. But the previous model we know about is GPT-3, and GPT-3 has 175 billion parameters. 175 billion parameters, where each parameter you might think of as one of these neurons. So you can think of the neural network as being 175 billion neurons. And for comparison, the human brain has about 80 billion neurons. So the neural networks that we're building today have more neurons than human brains have. They're not more sophisticated, they're not more complicated. In fact, it's actually quite shocking how little they can do with this many parameters. Nevertheless, these are huge systems. 175 billion parameters is a huge network. It's a lot of computations in order to train that network. And it's not even the biggest of these models. the largest model that I know about when I made this was Microsoft's Megatron Turing natural language generator, which is a 530 billion parameter model. So it's like half a trillion parameters. And I've heard people talk about GPT-5 being a trillion parameters, or other models being multiple trillions of parameters. So these are huge models. The computing impact of these models, it's very expensive to train these models. I think the figure that I know is from Facebook's Llama model. They spent 5 months training Llama on 2048 A100s. An A100, if y'all don't know about this, an A100 is the most sophisticated NVIDIA graphics card. It's the high-end business model of the graphics card. So this is not really a consumer electronics thing. To buy one of these A100s costs about $15,000 on eBay. So $15,000 to buy one of these, and Facebook used 2,000 of these to train its Llama model, which is also 175 billion parameters. And it was training for 5 months straight. So running 2,000 of those A100s for 5 months straight in order to train Facebook's language model. So it's hugely expensive in terms of hardware. It's also expensive in terms of carbon footprint. The amount of energy that you have to burn in order to run all of these GPUs in order to train one of these large models is very expensive. And we'll talk about some of these when we get into the AI ethics part coming up. But I just want to say a couple of things about how these models work, so you have some sense of what's going on with these models. So each one of these nodes is a neuron, and in machine learning models, they're typically feed-forward networks, which means you put the inputs on one end, and the data travels in one direction to the output. So again, this is not like how brains work. Your brain, as a neural network, is not just a feed-forward network, but there are all sorts of loops, feedback loops, in sort of cyclical circuits in actual biological neural networks. But in artificial neural networks, they typically, like you can make things that are recursive, but they're of limited functionality. All the big models that are actually useful are these feed-forward networks where you put in data on one end, and then you're getting output on the other end. And to train the model, what we're doing is we're training the weights, these connections, at each stage. So this is a feed-forward model. It's also important to note that it's a fully connected model. So you can see that this node on the input layer is connected to every single node on this hidden layer, right? So there's 4 connections going from this first input node to each one of the hidden layer nodes. And same thing for this next input node. It's connected to every one of the hidden layer nodes, and the next input node is connected to every one of the hidden layer nodes. And then each hidden layer node is also connected to every node in the next layer. If we had multiple hidden layers, then that would be a whole lot of connections. But here, this hidden layer is just connected to the output layer. And so there's only 2 connections, but 2 connections from each one of the hidden layer nodes. And so what we're doing is to train this network, is we want to find the appropriate set of weights for these different connections so that when we put some input, we're getting correct output. As I already said, an appropriately programmed feed-forward network like this can in principle be Turing complete or become a universal computer. But it matters what the weights are and what the configuration of the network is. So the whole object of machine learning is to figure out what these weights should be. So here's an example that actually shows all the weights. So here we have 2 input nodes, 2 output nodes, and we've got 2 hidden layers. Again, this is a fully connected feed-forward network. So every node in every layer is connected to every node in the next layer. So this node in this hidden layer is connected to all 3 nodes in the next layer, and so on all the way down the network. And then each of these connections has some weight. And just like in the perceptron, we take the input value and we multiply it by this weight in order to get this node. But this node is not just the input value on this first node, but it's also the second input value. So in order to calculate the value for this node, you want to take the input value for node 1 times the weight between node 1 and this node, plus the input value for node 2 times the weight from from input 2 to this first hidden layer node. In other words, this value here and this value here times the inputs will give you this value for this node. And you do that the same for each node on this first hidden layer, and then you do that the same for each node on the second hidden layer until you eventually get values on the output layer. So putting some value on the input and that input value trickles through all these network of connections until you get some value in the output layer. When you train a neural network, the first time you start with training, first time you start giving it input, you usually randomize the weights in the network. So you start off with a network with completely randomized weights. And if they're randomized weights, they don't really mean anything. And so the first time you put in inputs, you're going to get that input filtered by all of these sort of random weights, which means you're going to basically get a random value in the output. And that random value for the output isn't very helpful. What we want is the correct answer to whatever the input we gave it. So having the random value as the output is not very helpful. But what you do, and this is how machine learning works, this is an algorithm called backpropagation. It's actually maybe more helpful if we are back on this diagram. So what you do is you give it some input. That trickles through the network and generates some value on the output. And the first time you do it, because all the weights are random, that value is also going to be random. It's going to be junk, garbage in, garbage out. But you take that junk output and you compare it to the value that it should have given you, the correct answer, right? So I know what input I gave it, so I know what the correct output should be. And what I can do is I can compare the correct output, what I know should be the correct output, with the output that it actually gives me. So it gives me some value here. That value is just a random bogus value. But I can take that value and compare it to the value that I expect as the correct value. And then I can compare those two to get some difference. So the difference between the expected value and the actual value on the output. And I can use that difference as an error, as an error value in order to adjust the weights in the network. So once I get the error on the output, I use that error to slightly adjust all the weights. So I make a small adjustment to this weight by that error value. And for this weight and this weight, and in fact what I do is I go back through the whole network and look at every one of the weights and make a small adjustment to that weight based on the error that I get. This is the backpropagation algorithm. This is a sort of sketch of the backpropagation algorithm. It's really just a sophisticated way of doing a derivative, right? So the error value that you get on the output, you can think of that as like a derivative value that you can use to go back and make adjustments to the rest of the network. And so for this reason, backpropagation has people talk about machine learning as a kind of differential programming, because you're using these small differences in order to make adjustments to the network configuration. So this is how backpropagation works. Again, give it input, you use the output to generate an error value, and then use that error value to adjust the weights. And then you do it again. You give it a new input, and you get another error value, and use that to adjust the weights. And you do this over and over and over again. You do this thousands or tens of thousands or millions of times. And eventually you're going to get a network that has its weights pretty precisely tuned so that when you give it an input, it's going to give you the correct output, or an output that, of the sort that you expect. And this is how you train up one of these networks. This is what machine learning actually amounts to in the technical sense. So GPT-3 uses a version of backpropagation called stochastic gradient descent. Uses a sort of statistical technique to make it more sophisticated. We already looked at this. You can build these really large networks that get trained by adjusting all of the connections in each layer with that error value that you get in the output. And this is what you do to do machine learning. Here's a sort of example for exactly what we're adjusting the weights to, or like what do you mean by correct input and correct output. So this example is just of image recognition. So an image on a computer is made up of a bunch of pixels, as I'm sure you all know. So you can imagine that this image of this number is broken down into a bunch of pixels, where each of the pixels has some color value. Most of the pixels in this image are black, but there's some of these pixels are white, and some of them are different shades of gray. And so you imagine this is just a luminosity value for each pixel. So you can imagine putting each of these luminosity values for each pixel into a neural network as the input. Right, so if I'm giving this image as the input to the network, what I'm really doing is giving each node on the input the luminosity value for each pixel. And if this image has 784 pixels, then you can imagine 784 neurons as the input for this network. And then we want it to go through a couple of different layers so that it gives us correct output, and the correct output should be the correct identification of that number. And so you can see here that there are actually 9 output nodes, and we might number these 0 through 9. I'm sorry, there are 10 output nodes, and we might number them 0 through 9. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the idea here is that, so like imagine this is an 8, that this number is an 8. It's not a perfect 8. It's sort of an imperfect 8. But imagine this is an 8, and we put this value on the input pixels, and then the first time we run it again, all the network connections are, the weights are randomized, and so we're just going to get some random output value, but we know that the correct output value should be 8. So if this is the numbers 0 through 9, then we should have this node in the output lit up, and the other nodes not lit up, and that'll tell us that the output is 8. So that's what we want the correct answer to be, if we think that this is an 8. But maybe the first time we run it, it gives us a 4, and so we take the difference between a 4 and an 8, and it's going to give us some number, that's our error, and then we use that error value to go back and adjust the weights, so that next time we give it this image, it's more likely to give us the correct value that we want. And we do this with lots of different images. Every time we give it an image, it gives us some value, and we say, no, that might be what you think it is now, but actually the correct answer is some other value, and we sort of keep correcting it. This is the training part of the machine learning process, where it is originally giving us incorrect values, but we tell it what the correct value is, and we use that to make adjustments to the network so that it's more likely to give us the correct value next time. And again, if you do this over and over and over again for a big enough training set, you will eventually get a network that will give you a pretty good response, pretty good answer for every input. This is, you can think of this as an optimization problem. I'm going to skip over some of this because it's a little bit technical. But one of the videos I have in the talks is this talk from 2007 when Jeff Hinton was just a lone researcher at the University of Toronto. And Google does talks on campus, and they brought Hinton out to give a talk. And in this demo, Hinton shows an early version of his machine learning models that can correctly do this image identification task. And so you have a little machine learning model that Hinton demos that can tell you what the correct number is. And remember, Hinton is working on these for a couple more years, and eventually gets his machine learning models to beat the ImageNet classification task. And then gets hired by Google a couple of years after that. So this talk is really a little picture into the history as it develops. There's a really cool demo in this talk where he shows you how the model works, but it also gives a sort of high-level overview of how these models are being programmed or how they're thinking about these models from the people who are developing them. I also have in the slides a couple of videos that go over some more of the technical details about how these neural networks work. This 3 blue 1 brown video is pretty helpful. It gets pretty sophisticated, but if you're interested in some of the technical issues here, it's worth looking at. Another thing I have in the slides is the TensorFlow Playground. TensorFlow is the programming environment or programming language that Google uses to do its machine learning models. I'm actually not sure if Bard is Google's new machine learning model, but I'm not sure if it uses TensorFlow. It might. But what they've also done is this is the TensorFlow Playground, where they give you a little neural network to play with, where it's doing a classification task. So when I hit play, this neural network will start processing data. Here's the data in the data sets, and this is also going to be the output. And so what we want is for the machine here to draw some figure in this space that sorts out all the blue dots from the orange dots. Right. So again, it's just a classification task. Can you separate out the blue dots from the orange dots? And it's going to be doing this using this machine learning model, this little neural network, where here are the inputs, which are just the values of the data set. And then it goes through a couple of hidden layers until it produces the output, which is the figure that you'll see. So let me go ahead and run this once so you can see what it looks like. Yeah, so you see it got the answer pretty quickly. Now it's drawn a little shape that sorts out the orange from the blue. It can't really improve on that shape because it's the correct answer. And the way that it got this shape is by adjusting the weights between these neurons. So you can see that some of these neurons are bright blue. The weights are all some number between between -1 and 1. So the orange ones are the negative numbers and the blue ones are the positive numbers. But the weight is just some value between -1 and 1. This is 1.2 or -1.3. So I guess it might be normalized to -1 or 1. So remember when you start training a neural network, you start from a random state, and you can see this by every time I initialize a new network here. There's some slightly different configuration of the connections in the network. Every time you start it, it's always going to start from a random state. But then once I hit play, what's going on is that some of these connections are strengthened and some of them are weakened, so that it gets more and more accurate a result at the end. You can see how that happens. Yeah, so some of these are strengthened, some of them are weakened. You notice that the result that it gets here is not the same. It's not exactly the same as the result I got last time. The shape that it draws is slightly different. Let me do a different one, the different starting configuration. You can see again. Yeah, so now, like, it's still a triangular shape, but the rotation of that triangle is a little bit different, right? So every time it's getting a unique result. That unique result is a reflection of the fact that it's also generating a unique configuration of the network connections, right? So some of these weights are stronger than others, but there's not just one configuration of the neurons, the neural network. They'll get this correct result. In fact, there's lots of configurations. So if I run it again, you can see that we get a different shape, and we also get a different configuration of the weights in the network, that some of them are different from others. This is not the same result we got in the first one. And this is all meant to drive home the point that in some sense I'm not telling the machine what to do. I'm giving the machine a task and telling it to get the correct answer. But how it comes to that correct answer is kind of up to it and how it learns. And because every iteration of this starts in a different random state, they're all going to find different pathways to getting the correct result. So you can play with this demo. It's pretty fun. I remember teaching neural networks before we had this demo, and I'd have to draw all this stuff up on the board and do a bunch of mathematics on the board, and it was not very fun. But now we have these easy-to-use demos. It also gives you a couple of different data sets. This is like the hardest data sets. Very clearly not linearly separable. This is the kind of thing that a perceptron would struggle very, very, very hard with. But we can see how well our neural network here goes. And this neural network is also sort of struggling with this. You can see it's slowly improving over time. But it's not settled yet. And it's not doing very well. Obviously, this is not the correct solution. Some of these orange dots are being classified as blue, and some of these blue dots are being classified as orange. So obviously, it doesn't have the correct answer, but you can see that it's adjusting its solution over time to try to improve. But it's doing it very slowly. Part of the reason it's doing it very slowly is because this network is not very sophisticated. It only has 2 hidden layers, and we're also only considering 2 input features. So one thing you can do, and this is why this demo is kind of fun, is you can add more features to consider on the input. You can also add more hidden layers and more nodes on each layer, so we can make a more sophisticated neural network. Now let me see what happens if I just run this. So because there are more neurons and more layers, it also means that the network can go through more sophisticated configurations of its eventual solution. So you can see that this pattern is not something that was able to be generated before I added all these additional layers. So we have more sophisticated patterns. It still doesn't have the right answer, though. Right? This is an orange, but it's being classified as blue. These are orange, classified as blue. I guess these blue are classified as orange. So it's not perfect yet, but it's improving slightly, slowly over time. It's actually not improving fast enough for me. Let me come back here and make this a little bit simpler. I'm also going to add a little bit of noise. The noise helps it not get caught in a local optimum, which is one of the challenges of this kind of gradient descent learning process, is that you can get into a configuration where it's not an optimal configuration, you don't have the correct solution, but making just small adjustments to the network weights actually makes the solution worse, not better. This is the local optimum, and it's part of the challenge of doing backpropagation learning in this way, that you're only generating a very small error signal, but sometimes you need a much larger error signal in order to find the correct solution. And so one way of dealing with this is by adding a little bit of noise to the system, so it checks sort of nearby areas without getting stuck in any one place. And this is why you can see it sort of bouncing around and sort of jittering around. You might think this is kind of anxiety, a sort of unsettledness about what the solution is. It doesn't know exactly how to improve its solution. It's trying a bunch of things. I'm not telling it to try these things. It's trying things out on its own. and observing the results and then making adjustments on the basis of those results. So this is good. It's got the blue ones here. It's got these orange ones here doing pretty well. Some of these blue ones here are not getting caught though. So this can take a while depending on the configuration of the network and depending on the starting state. So I'm going to go ahead and stop here. But I encourage you to all test out this TensorFlow playground because it's fun. It's fun to work with. So just to get a bit of a handle, some intuitions about what the neural networks are doing and how they're learning. So like I said, Geoffrey Hinton beats ImageNet in 2012. And in order to beat ImageNet, I guess that's the next video. Yeah, so this is ImageNet. ImageNet is just a bunch of pictures that are labeled with what they contain. And the goal for this task is to associate the image with the correct label. Some of this is a little bit confusing, right? So this is a dog with cherries. The correct label for this image was cherry, but the system guessed Dalmatian, which was incorrect for the ImageNet test. Similar over here, the correct label was grill. So it's not trivial. It's a little bit of an awkward test considering what machines can do nowadays, but it's just associating the image with a single label. This was again an unsolved problem. There were systems that did poorly on it, and nothing did very well. But Hinton in 2012 showed a machine that was able to do this classification task in a pretty sophisticated way with a pretty high success rate. And in order to do this, Hinton used this technique called convolutional neural networks. So a lot of the advances in machine learning over the last couple of decades has been in ways of making the computational task more efficient. Right? If you're calculating the network, the connection weights for these really huge networks, the computational task quickly becomes extremely difficult. And so there's a strong motivation to find more efficient ways of doing these computational tasks. And one of these ways is using convolutional neural networks. So instead of taking every pixel in the entire image, what convolution does is it's a sort of a clever way of grouping different parts of the image together. And the idea is that you run these convolutions in order to get these little sort of components of the overall image. And then you can run those components through a fully connected feed-forward network. And then get some result for that little component. And then the convolutional network algorithm tells you how to incorporate those results back into back with convolutions in order to get some result for the entire image. So it's a little bit of a sophisticated way of doing it, but it makes the computations a lot more sophisticated. And this is why Hinton was able to beat ImageNet in 2012. And like I said, shortly thereafter, Hinton gets picked up by Google. Yann LeCun, who developed the convolutional networks, get picked up by Facebook, and then lots and lots of investment and development until these models start getting released in the last year or so. So that's basically where we are today. The last thing I want to talk about, I know I'm already over an hour, but hopefully this is useful. The last thing to talk about here is some of the ethical concerns with these machine learning models, these large-scale machine learning models. And there's a lot of concerns to raise, a lot of concerns worth talking about. There are some concerns about the training data that's used on these systems, where that data is coming from. Is that data protected by copyright claims or other sort of intellectual property rights? Is that data trustworthy? Is it from a trustworthy source? These are all sort of concerns about where this data is coming from and how it's being used. There's also concerns from AI ethicists about biases in that data, whether that data can be trusted, and how poor data sources might be used to further examples of injustice. And we'll see some of these in just a second, but these are cases like using machine learning algorithms in risk assessment for, say, loan applications or for criminal sentencing, see how long a criminal is told to stay in jail or in prison. These kinds of things are already being decided by algorithms. When you apply for a loan, it's probably being classified by a machine learning algorithm to decide whether you're qualified to have that loan. When you apply for jobs, especially in the tech sector, it's very likely that your applications were screened by some machine learning algorithm. When you apply to colleges, basically just about any application that you give for jobs or loans or these kinds of things, are being assessed by these machine learning algorithms. Not just that they can be assessed in the future, but they're already being assessed in the present. So there's concern about whether this training data is biased, whether the algorithms are actually being used in biased ways or in ways that are exacerbating certain kinds of injustices. How fair the algorithms are, but also how transparent they are. Do we know how they operate? Is there any kind of oversight or regulation on their operation? Who's accountable when the machines do something wrong or put someone in danger or cause some other kind of harm? Right, so these issues of transparency and accountability sometimes get talked about in terms of explainability, like can you explain what the machine model is doing? For these really large, 175 billion parameter models, it's sometimes very difficult to say how the machine operates internally and how it's generating the decisions or results that it is. And these are often things that we would like to know. Like, for instance, if I'm applying for a loan and my loan application is rejected, I'd like to know why, so that next time I apply for a loan, I can avoid that mistake. Is it because my references aren't good, or because my collateral isn't sufficient, or what was the issue? And part of the worry is that if we're just using these machine learning models to generate a result, and the machine learning models are these big hulking models with so many parameters that it's really hard to tell what's going on, then we don't really have an explanation for why the machine came to the results that it did. And that doesn't help me very much when my loan gets rejected and I don't know why. So especially when these models are being used in critical infrastructure that has direct impact on human lives, we want to know that it's being that its operations are explainable, that there are people that can be held liable, that there's sufficient oversight and regulation to make sure that they're being used in a fair way, and this kind of stuff. I've also mentioned issues around energy use and carbon footprint. Where's the energy being used to train these models? How are we getting this energy? What is its environmental impact? For this reason, I'm sorry. The new machine learning models, when there's publications on them, it's become part of the scholarly expectations that they also post carbon footprints of the training. So how much carbon was emitted in order to train these models, and because of this, because there's this sort of professional expectation that the companies are talking about their carbon footprint, there's also been pressure to make the carbon footprint as low as possible, and this is undoubtedly a good thing, so that we're not using AI in a way that is just environmentally reckless. It's also done things like it's encouraged people to build data centers and these processing centers near nuclear power stations, because nuclear power stations, the energy that you use from there has a very small carbon footprint, and so it makes your model look more environmentally conscious when you have such a low environmental impact. This kind of thing. So these are all issues in AI ethics, sort of from a technical standpoint of how the models are being trained and developed and deployed. There's also the use and misuse of these models that has had a lot more conversation in the public media. So things like disinformation or misinformation, these deep fakes, using AI-generated images or AI-generated content in order to fool people into thinking like news events, like when Trump was arrested, which didn't actually happen, but there's a lot of images online of Trump being arrested that are generated by AI. The machine learning models like ChatGPT also just give incorrect results quite frequently, and it'll speak in a way that's very confident about stuff that it just made up. These are called hallucinations, when the machine produces data that it treats as fact, but in fact is not a fact, but is just something that's just made up. I know a lot of academic scholars, when they put their names into ChatGPT and say, what has this person published? And it'll just give back a bunch of bogus citations. Sometimes they're real citations for other people, but sometimes they're just not real citations at all. Right? These are the hallucinations. And it contributes to a corroded or corrupt or untrustworthy information environment or knowledge environment. And we've seen how these kinds of things can have impact on, for instance, political elections. and other sorts of public policy issues. So this is also very troubling. The use of these algorithms and their impact on people's lives today. These are all issues that get talked about in the AI ethics literature. There's also a fairly big part of the literature that talks about policy and what policies should or shouldn't be instituted, what kind of regulations are necessary for keeping these applications safe and in the public interest. Right now, there's very little oversight or policy or regulatory frameworks for talking about AI. The White House has put out some press releases that really don't have a lot of legislative authority, because there's really just not a lot of regulation, both on AI and machine learning, but also on the tech industry generally. Like, there's still very little policy and regulation over the social media companies, like Facebook. And they made it through the last decade without almost any regulatory oversight at all. And these same companies, these same unregulated companies, are now responsible for developing these AI systems, also without regulation. This isn't the case. The lack of regulation isn't universally the case. The European Union has some regulatory frameworks. We'll talk about that in just a second. But actually, before I go into any further details here, it's probably worth giving some examples of AI ethics. So this is not an AI example, but this is a tech example of the sort that maybe is relevant for thinking about algorithmic bias or machine bias.
Nice. Okay, Noel, we try now. One to your hand. Two black.
Two black.
Yeah.
What I'll
Come
do?
again. Come again, Sashi. Nah, you two back over way.
What I have to do to get
what you have to do
this is how racial this thing is.
Yeah.
I have to use that piece of white. Let's say napkin and show again. What's the difference?
Put your napkin again.
Napkin again.
Right, put your hand now.
What's the color in my hand?
Man, the black man getting fight all over.
Okay, so the claim here is not really. I mean, calling the soap dispenser racist is a little bit tongue-in-cheek. The soap dispenser obviously doesn't have any thoughts about race at all. But you have the discrimination from the soap dispenser, where it's not recognizing black hands as hands that it should dispense soap to, and it's probably also not the case that the people who designed this soap dispenser were intentionally being racist or trying to discriminate against certain skin colors, skin pigments. But they built a device that did that anyway, so it probably wasn't their intention. What's probably the deal here is that the people who built this probably were themselves white, and probably no one with black skin was in the development and testing of this device. And so when the developers and testers used it, it seemed to work just the way it's supposed to. And so they thought there was nothing wrong with it. And so part of the issue here is not an intentional sort of racism, but it's the sort of implicit racism that comes from a field that is not very diverse. This is one of the reasons why diversity is so important. We talk about this a little bit in lesson 2, way back when. Right? If you don't have a diverse cohort of engineers developing these and testing these devices, then you don't know how they will play out when used by the diversity of actual human beings. Right? So if everyone who built the soap dispenser is white and is only testing it with their white skin, then they just don't know how it's going to respond when you put it in the real world and have to deal with the actual diversity of people's skin color. Right, so this is a sort of a toy model of the more general problem of bias in AI. The better example of this is from Joy Buolamwini. I'm not going to play this whole TED Talk, but Joy Buolamwini was a grad student in AI at MIT and was trying to do some research in facial recognition software, and she found... Sorry. Joy Buolamwini found that when she would sit in front of the facial detection software, it just never detected her face. it just did not know that she had a face. And if she puts on the white mask, then it finds her face immediately. So these facial detection algorithms are using certain indicators of facial structure. So they're looking for like eyes and noses and cheekbones and so on. But they're assuming that you can spot these by looking for shadows and this kind of stuff. But those techniques don't really work when you're working with black faces, where the shading and the illumination are just going to be different than white faces. And so what Joybal and Winnie found was that not just this one bit of software, but actually software from all of the major tech companies had this sort of systematic blindness that was not able to recognize the faces of people with dark skin. And lots of people have dark skin, and so what that means is that a lot of this software just did not work for most people. And this was problematic, especially when these companies are promoting the software as being highly accurate. And it is really accurate if it's looking at white males' faces, white men's faces. It is pretty accurate. The software that she was testing had over 90% accuracy when looking at white men. But when looking at black women, it had a very low accuracy to the point where it sometimes wouldn't even recognize that there was a face in the image. So this is bad. It's bad just to make the biased software, but it's especially bad when you think about how the software is being used. So IBM, for instance, was selling its facial recognition technologies to the New York Police Department, where the NYPD was using these facial recognition technologies in order to detect criminals. In order to, not even detecting criminals, the NYPD was using these at like major sporting events at Madison Square Garden. They would set up cameras outside and just tag everyone's faces. They were using them to spot known criminals at protests during the Black Lives protests, for instance. The NYPD would come out with cameras on big sticks and just take pictures of everyone, so it knew who was there. So it's already concerning how the extent to which the NYPD uses surveillance to monitor citizens of the city. But it's even more disturbing when you recognize that software is fundamentally biased and is simply not accurate with a large portion of the population, especially when that population is disproportionately targeted for police harassment and abuse. This kind of stuff all adds up to some concerning issues. So I have the TED Talk from Joy Buolamwini, but she actually is also the I'm going to go ahead one more slide. Two more slides. Buolamwini is also one of the main focuses of this Coded Bias documentary from PBS. I also believe it's on Netflix, and you can watch it there. But Joy and a bunch of other AI ethicists talk in this documentary about the harms of algorithmic bias and give some more detailed examples of the sort of things that we've been talking about. Let me come back here. Joy Buolamwini and Timnit Gebru also published this very famous paper called the Gender Shades paper. It was sort of grounded on this work on facial recognition. But what they realized is that part of the problem, part of the reason that this big tech software doesn't work for recognizing faces is that the data sets that they're training the software from is also heavily biased, largely drawing from white men, a few white women. And so one of the things they do in testing the software is not only do they test the software, but they also generate an alternative data set where the data set is I'm bad at slide decks. The data set that they use, so they compile a new data set that was supposed to be more equitable, and they use images, portraits of politicians from several different countries around the world, especially several countries from Africa, but also from Europe, so that you have sort of a more full picture of the diversity of human faces to better train the software on. And so not only do they find that the big tech company facial recognition software is really bad at detecting especially black women faces, but that when you give it the appropriate training data, that you can do a lot better. So this is the big result in the gender shades paper. It was a sort of landmark paper that got people to pay attention to this algorithmic bias issue more closely. Sorry. Yeah, and this is talked about in the coded bias documentary. Another really important paper that comes out around the same time is this ProPublica machine bias paper. ProPublica is a investigative journalism outfit, and this is a 2016 paper where they talk about how this machine learning software called Compass is already used in several states, lots of states in the South, but really states all across the country. I think it was like 11 states when the article was written, and it's probably more since. But that several states already use a machine learning software in order to do criminal sentencing. So criminal sentencing is after someone has been found guilty of a crime, then you have to decide how long they go to prison, or what the fine will be, or what the sentence will be. And a lot of people, there's a long-standing worry that judges are biased in handing out sentences, that judges tend to give black people stronger sentences than white people for lesser crimes. So there's already a significant pervasive worry that judges issue criminal sentences in this biased way. And this is one of the motivations for going to a software alternative, right? The idea is that, well, the software can't be biased. The software is just doing something algorithmically, so it shouldn't come up with a biased result, and so we don't have to worry about racist judges. The issue is that the Compass software is trained on the history of criminal sentencing. So they looked at how real judges decided thousands and thousands of cases, and what the sentences were in those cases, given their crime. So to be clear, the software here is not using race to determine how long someone should stay in prison. It's using these other factors, including their arrest history, their conviction history. Nevertheless, because it's trained on the history of what judges have actually of real judge sentencing, the software replicates those same biases. So they give a couple of examples in the text. So in this case, here's Vernon Prater being scored a low risk and given a light sentence, whereas Bishop Borden is being scored a high risk. But if you actually look at their case history, Vernon Prater had prior offenses of 2 armed robberies and 1 attempted armed robbery. And then after being sentenced here, Vernon Prater goes on to commit another grand theft. Whereas Bishop Borden, her prior record shows 4 juvenile misdemeanors, and Bishop Borden did not go on to commit any additional crimes after being sentenced. Nevertheless, the software judged Bishop Borden high risk and Vernon Prater low risk. And you might think that this is exactly the opposite result that it should have gotten. It should have judged this guy much higher risk and should have judged Bishop much lower risk. But the reason it didn't is because this is how actual human judges would have decided this case also, or would have decided these cases also. In other words, the Compass software is, to some extent, accurately replicating this history of criminal sentencing. And the problem is not that the machine is biased, it's that the history of sentencing that it's trained on is biased. Right? And it's merely repeating or echoing what the judges would do in those cases. And if we're already worried about the judges, then we should be equally worried or even more worried about the software. One reason to be more worried is because once it's in software, it becomes a lot harder to change. Like a judge eventually retires, right? Old judges will die. But Compass, I mean, like in some, especially in the public sector, especially in government operations, there are some technologies that are from the 70s or even earlier, they're 50 years old. Not because they're the best hardware, but because it's really hard, especially in public service, to change these kinds of technologies or to adopt a new system. And so once you adopt a system, that stuff tends to get pretty deeply integrated and pretty hard to change, right? So training a machine to replicate the history of criminal sentencing and then having a machine take over that task means that it becomes a lot harder to recognize where the biases are and to stop them from happening. Indeed, a lot of people are just going to say, well, because it's an algorithm, it's not going to be biased in the same way that a human is going to be. And so they're going to trust the algorithm more when, in fact, they shouldn't trust it anymore at all. but it's that appearance of trust. It's that appearance of a lack of bias that is part of North Point's selling point, right? This is how North Point is going to these different states and these different jurisdictions and getting them to buy the software, because it's trying to convince people that this stuff is actually a lot more safe and fair than it is. So we're already living in an era, and we have been for several years now, for running almost on a decade. We live in an era where machines are already responsible for sentencing criminals, for deciding how long people spend in prison. Right? This isn't some far future science fiction scenario where machines are way more intelligent than us. This Compass machine is not more intelligent than anyone. At best, it's just parroting what human judges do, and that's already problematic enough. But handing over this kind of power to the machines seems unwise. So look at the documentaries. Look at some of these lectures from Bender on dehumanization in the age of AI. There's some interesting stuff in these lectures, and think about some of these questions, like how are these algorithms being trained? How are they being used? Where is the data coming from? Is it operating in a way that aligns with our expectations and values? Or in the sense of, would we expect a human to perform these operations in the same way or in a different way? Can you explain what the machine is doing in a way that makes sense, in a way that in a way that makes sense, in a way that's compatible with existing legal and regulatory frameworks? These are sort of open questions. Questions worth asking of these machine learning models. You can also ask about the social and environmental impact of these machine learning models, like who's using these systems, what is the impact of their use, how are individuals or communities impacted by their use, to what extent is this impact taken into account. A good example of this is with ChatGPT. It was released, and every student across the country, it was released like a couple of weeks before finals in November of 2022. And students all across the country realized that this stuff can be used to help them take their finals, to help them cheat on their exams. And OpenAI, the company that made ChatGPT, didn't really have a plan in place for what to do about extensive plagiarism or how this might impact the educational system. It was after they released ChatGPT that they started talking about watermarking. This is a way of making sure that the machine is producing words in such a way that you can tell that it's being produced by the machines as opposed to a human. And there have been some attempts to produce this watermarking technologies to help make it detectable whether something is produced by ChatGPT or not. But there's also been some results recently that suggest that watermarking is not a viable strategy in the long run, and it's actually pretty easy to defeat watermarking. So it's really hard to tell whether the material is being produced by a machine or a human. But again, OpenAI didn't take any of this stuff into account. It just released the system and let the chips fall where they may. This has been a pretty big headache for people who work in education like myself, who've had to deal with cheating around ChatGPT. There's also been lots of complaints, especially from the artist community, about how this might impact art. People are less willing to pay artists to construct art if you can just get an algorithm to do it for free or for very cheap. We've already talked about some of the misinformation hallucinations. ChatGPT also produces things like instructions for making bombs or how to conduct terrorist attacks, this kind of stuff. And maybe we don't want an easy source of information for how to build bombs and conduct terrorist attacks. ChatGPT also is liable into hate speech or misogynist speech, racist speech, this kind of stuff. So all these things are problematic. All these things are things we still have to work out and deal with in some way. But we're still in the early stages of these technologies, so it's not clear exactly what happens next. Maybe regulations are around the corner, but we're not there yet. But it's also good to think about what kind of regulations would help, whether those regulations would be effective, how to make them effective. And like I said, there's almost no regulatory framework in the United States for managing machine learning models or even like social media, big tech companies. So they have a lot of power in their hands, and they have a lot of power in their hands, and there's a lot that they can do. And right now we're basically in a situation where we have to hope and trust that they act in our public interest. But of course, they're companies, and as we've seen in this class, you can't always trust the big companies to have the public interest in mind. The closest we have to the regulatory framework is in the EU. The EU has the GDPR, which is the General Data Protection Regulation. It's the strongest form of digital protections that really exists anywhere on the planet, and it's been around for a while, and it has a lot of consequences. So you know how websites nowadays make you ask if you want cookies or not? The reason that it does that is because it's one of the GDPR provisions that people should be able to opt out of having cookies. So that's a legal protection that exists in Europe, but because a lot of these tech companies, even tech companies that aren't based in Europe, they still want to operate in Europe, and so they have to institute these features anyway. So the U.S. Happens to benefit from a lot of these GDPR provisions simply because tech companies are rolling it out for all of their software. But the U.S. doesn't have a way of actually enforcing those provisions the way that the EU does. So there's some hope that the EU GDPR will also be expanded to include machine learning models and some protections there, but we don't know yet. Like I said, it's April 2023. I think just this weekend, Italy banned ChatGPT, and OpenAI had to shut down access to anyone in Italy to ChatGPT. And if Italy's a member of the EU, and so it might be that Italy's policies here trickle out to the rest of the EU, but no one knows yet. We'll have to see. Okay, I've already talked for 2 hours, so I really need to stop here. I hope some of that was interesting and informative. There's clearly a lot more to say, and I could go on for several more hours, but I'm going to stop here. And good luck with that material. Hope you can find some interesting things to say about AI, and we'll keep talking about this next week. All right, thank you, everyone. Bye.